Welcome. Thank you for tuning in today, where I will be telling you about Venus's past thermal conditions as we can understand them through the mechanics of multi-ring basin formation. Before we get started, I would like to thank my co-authors, Brandon Johnson and Alexander Evans, for their help and guidance with this project, as well as many others. And let's get started. Studying Venus is interesting because at first glance, you may expect it to be very similar to Earth. The two planets have similar sizes and masses, and orbit our Sun at generally comparable radii. However, the current stifling conditions on Venus clearly indicate that the two planets have undergone very different evolutionary paths. Because of this, questions about Venus are usually trying to understand its geologic history and why it is so different from Earth. There are limited global datasets for us to use to study Venus because of the extreme surface and atmospheric conditions, but one dataset that is available for us to use is the impact crater record. On Venus, there are about 1,000 impact craters, and they're distributed across the surface in a seemingly random distribution. And researchers have been using these impact craters to try to answer a lot of the geologic questions that we have about Venus's past. These are questions like, when was the last time Venus was globally resurfaced, and how often has it been resurfaced throughout time? How active is the planet now? Do we see any evidence of volcanic embayment on fresh craters? And one of the questions that we're trying to get at in this study is there anything that these impact craters can tell us about the thickness of the Venus lithosphere? So to answer that, we went straight to the biggest impact crater on Venus, Mead Basin. Here's a picture of Mead. Mead is the largest impact crater on Venus, and it's characterized as a multi-ring basin, which I will get into in a few minutes. What's really important for the purposes of this study is its two main ring faults. It has an inner ring fault at about 190 kilometers diameter, and an outer ring fault at about 270 kilometers diameter. And this area shown in red between those two main faults is known as the terrace zone. And inside the terrace zone, there's still some faulting going on, but it's smaller scale, and the faults aren't nearly as coherent as they are for those two main ring faults. So we're going to use these ring faults to try to understand what is going on in the Venusian lithosphere. But to understand this, we need to back up just a little bit and talk about impact craters as a concept. Here I'm showing you the different kinds of craters that we observe on different terrestrial bodies. They range from the really small, which are simple craters and have a nice rounded floor, up and as you get larger, you go into complex craters with an uplifted central peak, then peak ring basins, which are bigger than complex craters, and instead of a central peak, they have an uplifted ring around the crater floor, and then finally multi-ring basins. Multi-ring basins are categorized by ring faults, which extend all the way around the crater basin and extend deep into the planet's surface. The main hypothesis for multi-ring basin formation is known as ring tectonic theory. Ring tectonic theory is a really useful way to relate the morphologies of these multi-ring basins that we observe on different planetary surfaces with the geologic conditions that were present when they formed. So in both these cases, here on the left and the right, assume that the impact is approximately the same size. But on the right-hand side, we have a thinner lithosphere, and on the left-hand side, we have a thicker lithosphere. As the schematic illustrates, you expect to have different multi-ring basin morphologies for similar-sized impacts depending on how thick your lithosphere is. So this is the principle upon which we're going to try to understand how the ring faults of Mead Basin relate to the Venusian lithosphere and what it's telling us about how thick it is and what kind of thermal conditions existed at the time of impact. So now I'm going to get into my model. We use the shock physics hydrocode ICL2D for this study. Our cell size is 500 meters. All impacts strike the surface at 17.5 kilometers per second, and we vary projectile size between 24 and 36 kilometers diameter. Compositionally, we use a basaltic projectile striking a target comprised of a basaltic crust and a dunite mantle. We vary crustal thickness between 20 and 30 kilometers. The primary variable we tested was temperature, and to do so we varied the lithospheric thermal gradient between 3 and 25 Kelvin per kilometer. This gave us a range of possibilities from a cold lithosphere up to Earth-like conditions. We tested surface temperatures of 723 and 350 Kelvin. In all cases, the convective mantle is set to 1400 Kelvin. Here are a couple of examples of temperature versus depth and strength versus depth plots showing how these quantities vary for different thermal gradients. We note two key takeaways. First, higher lithospheric thermal gradients indicate thinner lithospheres, as illustrated by these color-coded lines. Second, a related observation, higher thermal gradients substantially weaken the crust and upper mantle. What I'm going to show you next is a few key time steps to really illustrate the principles that are at work when we evaluate these ICL models. So the parameters that I use are listed in the top left box here, and what's really key is that as we progress through the model simulation, the faults that we expect to see that are analogous to the Mead Basin ring faults are going to pop out as a nice light yellow color, and I'll go through and point them out as the simulation progresses. Here we have one of the first time steps that illustrates how the basin looks when the transient crater is opening up, just 15 seconds after impact. This image here at 105 seconds post-impact shows the crater during the crater collapse stage where the floor is moving upwards in response to the unstable shape that the transient crater had, and we still have no ring faults forming. Here in this image, taken at 180 seconds post-impact, we can see that the first beginnings of our outer ring fault have started to form at about 150 kilometers radius. Here at 220 seconds post-impact, we see that there are several faults forming near that outer ring that I identified earlier, but what is really key here is that we have started to begin to form the inner ring faults, here coming in at about 100 kilometers radius. Here at about 300 seconds post-impact, all of the ring faults that we are going to develop have already formed, and you can see that there's been significant motion along those fault planes as identified by the increasing total plastic strain. Here at 400 seconds, we have ended our movie, and all of the faults that are going to form have done so. So even though the basin isn't quite finished forming, all of the parameters that we're looking at for the purposes of this study have formed and will be pretty consistent for the rest of the simulation. So next I'm going to show you what the movie looks like when we play it at full speed. You're going to see all those main stages hit with the transient crater opening up, then the crater collapse stage, and then the ring faults forming. So I'll let that play 2 times through. Now, I'm not going to go through and show you videos for every single simulation that we did because that was a lot, but I will tell you that the mechanics that we observed in that one simulation are pretty consistent for all the thermal conditions that we tried. We found that if you have really cold conditions, so you're down in like the 3 Kelvin per kilometer, 6 Kelvin per kilometer lithospheric thermal gradients, you actually really concentrate your fault formation close to the basin center, and your basins don't actually really get big enough, or if they do, they don't form the ring faults that are as far away from the basin center as we observed with Mead. And on the far end, if you have really high thermal gradients, you have like 20, 25 Kelvin per kilometer, then you actually don't form the inner faults, and you actually, instead of forming the lithospheric ring faults farther out, you get more of a diffuse fault zone. So you actually don't match conditions on either end when you have really high thermal gradients. And this is really critical because it gives us confidence that we actually successfully bracketed our results. The run that I showed you is for 10 Kelvin per kilometer with a 36 kilometer projectile, and we actually do form the faults in the expected locations, and we feel really good about that because if you go colder, then you don't form the faults in the right spot, and if you go warmer, then you may not form faults at all because everything is too ductile and it just flows. So that was really interesting. But Evan, I have a question. What if Venus wasn't that hot in its past? We don't know that Venus was always 723 Kelvin at the surface. How does that change your results? That's a great question, other Evan. Let's get to it. So as part of this project, we looked at a lower surface temperature of 350 Kelvin. And we found that when you have a lower surface temperature, you are able to accommodate higher lithospheric thermal gradients and still form those ring faults in the expected locations. This slide illustrates where the inner and outer ring faults form as a function of different crustal thickness and projectile size. What's really important when you look at this graph is that as you move upward on the x-axis, you increase in lithospheric thermal gradient. And what we find is that as you increase that lithospheric thermal gradient, all of your ring faults will form at a higher radii. And at some point, either your inner ring fault doesn't form at all, and your outer ring fault, instead of forming one distinct fault, will end up as more of a diffuse zone and then really doesn't count as a ring fault at all because it's all just dipole deformation. So the red lines and the red symbols on this plot correspond to the 723 Kelvin surface temperature. And then if we add the 350 Kelvin surface temperature right now, we can see that as you lower the surface temperature, you actually get similar results, but for relatively higher thermal gradients. So whereas with a higher surface temperature, we find that really the maximum thermal gradient that is consistent with Mead Basin formation is about 10 Kelvin per kilometer. When you decrease the surface temperature down to 350 Kelvin, then you actually bump up the consistent lithospheric thermal gradients all the way up to 14 Kelvin per kilometer. So this is really important, and it really underscores that interplay between how the thermal conditions are affected by not only the surface temperature, but also the lithospheric thermal gradient. And there's a bit of a balance going on between the two that we can see in the results here. So how do these results inform any kind of comparisons that we can make between Earth and Venus? Here I am showing the highest lithospheric thermal gradient that we found was consistent with Mead Basin formation of just 14 Kelvin per kilometer, and then an average Earth value of 30 Kelvin per kilometer. Now, Earth is very heterogeneous and has mid-ocean spreading centers and thick continental crust. So this average Earth value is not meant to represent just the continents or just like a mid-ocean ridge, but rather is a global average value, which is clearly an oversimplification for our beloved planet. But then if we take this simplified average and we assume that both planets are covered in basalt with a thermal conductivity of about 2 watts per meter per Kelvin, then we can back out what the superficial heat flow would be on average for both of these planets, Earth and Venus. And when we do that calculation, we get that Venus should have an average surface heat flow of about 28 milliwatts per meter squared, and Earth should have an average surface heat flow of about 60 milliwatts per meter squared. Great. Now what? Well, now we go into the literature. So if you look at some papers that were done back in the 90s looking at types of lid tectonic regimes, which is one of the main ways that people try to characterize the geologic activity of Venus, Solomatov and Marisi in the 90s went and looked at what these superficial heat flows would indicate for different kinds of tectonic regimes. So you can have a stagnant lid where your lid is very thick and is resistant to the mantle deformation at depth, or you can have an active lid where the mantle is convecting and your upper lithosphere is relatively thin and is able to be deformed by that underlying mantle convection. And the cutoff that they found actually is about 50 milliwatts per meter squared, which is consistent with these findings and what we currently at least estimate for Venus and what we know about Earth. So Earth would be above that limit, so it'd be more likely to be in an active lid regime. So even though we took an average value and we stuck our really thick continental crust with our really thin oceanic crust, we still get that Earth should be this active planet. But then when we look at Venus, the values are really still too low. So we would expect that Venus would be more in a stagnant lid regime, which is consistent with what we currently understand about its surface features and any kind of geologic processes that are going on there. But there's still a lot of active research trying to understand, is Venus actually in a stagnant lid regime? Is Venus got some other kind of active lid that we just don't recognize because it is a different form than our beloved plate tectonics? So I'll just quickly recap and go through some quick conclusions. We find that we are able to replicate Mead Basin using ICL numerical simulations, and that we can replicate this basin with thermal gradients up to 14 Kelvin per kilometer if you drop that surface temperature, which it could have been much lower in its past. Then if we look at the implications for these lithospheric thermal gradients, we find that Mead Basin indicates that Venus would have been in a stagnant lid regime at the time of formation. This is really important because the lid tectonic state of Venus is one of the main questions that we're always trying to understand when we look at this planet. And then finally, although Mead Basin is only one data point and we understand that, there are other smaller but still multi-ring basins across the surface of Venus that are pretty evenly spaced, they're not clustered, that suggest that the thermal conditions that would have been present when Mead Basin formed were also present at the time that those basins formed. So we have some good reasons to think that the conditions that we find for Mead Basin would have been somewhat consistent throughout Venus's past, and this isn't just like a one-off kind of spot that we found. So with that, I would like to thank you for listening to my talk and just acknowledge the developers of iCell2D and PyCellPlot, which I used extensively during this work. And I would also just like to say, if you are interested in learning more about this project, it was recently published in Nature Astronomy. So here's a QR code that you can scan with your phone and it'll pop you right over there. So you can download the manuscript. And one last thing before I let you go, I am on the hunt for a postdoc. I anticipate finishing up my PhD sometime in late 2021. So if you are interested in collaborating, if you're interested in getting to know me a little bit more, my website is evanbionis.com. There's a QR code there you can scan with your phone. They'll pop you right over there, and I would love to hear from you. Thank you very much. Bye.